with colligative properties. We've done the concentrations. Now we're going to look at the effects of particles in solutions. So when we start, we're going to look at the physical properties of solutions. First off, well, it helps if you can write with your pencil. So here we go. We need non-volatile solutes. And again, spelling is optional today, evidently. Okay, so solutes. Now, what are these? These are ones that have low to no vapor pressure above them. These are solids like sodium chloride, sugar, calcium chloride. So solids that do not evaporate off. Okay, and the net effect is what it does is it lowers the vapor pressure of a solution. And we'll look at a practical counting of that for those people who like to visualize. Now, so if colligative properties are a function of non-volatile solutes and they lower the vapor pressure, there's one other issue you have to worry about is it's a function of the concentration of the particles present. Now the trick to this is we don't take the original solution per se. Okay? We don't care if they are charged, neutral, large, small, molecular, what their size is, don't care. We only care about the number. So, if we have a particle and it can break up into multiple pieces, then we worry about the multiple pieces. We don't worry about the particle initially. So what this truly means when we get down to it is if we look at C2H22, this is sucrose, this is table sugar. Okay? And if you look at the sucrose, then what you end up with is 1 mole of particles for every 1 mole of sucrose because this is a non-electrolyte. Now remember from general chemistry what a non-electrolyte is. It's a molecular compound. So when it hits solution, it doesn't dissociate. On the other hand, sodium chloride is an electrolyte. That means when it hits solution, you end up with 2 moles of particles, 1 mole that's sodium ion, and 1 mole that is chloride ion. So 1 mole of sodium chloride has, colligative property-wise, has an effect of 2 particles. Calcium chloride is again another electrolyte. So when it splits up, you're going to get 3 moles of particles, 1 mole of calcium ion, and 2 moles of chloride ion here. Electrolytes, remember, are salts. And all of these are salts because they have metals. So 1 mole of aluminum chloride would produce 4 particles because it's 1 mole of aluminum plus 3, that's 3 plus 3 moles of the chloride ion. So when we look at species, with respect to colligative properties, we've got to look at the number of particles, what they are and what they're going to do. So for example, what is the concentration of the following solutions in colligative property calculations? Well, basically what that means is you're going to multiply by the number of particles that are present. So for example, sodium chloride is an electrolyte. It's going to dissociate into 2 particles. So with respect to colligative properties, we're going to have 0.3 molal. if we're looking at ammonium phosphate, if we look at that, we've got 3 particles here, 1 particle here. So we're going to end up multiplying it by 4. 4 times 4 is 16. Carry the 1. So 1.36 molar, if you're talking about colligative properties. Now, this one is interesting. If you look at it, you're like, wait, it's not got the ammonium ion. I don't recognize anything in it. It's all nonmetals, so this is a molecular compound. Happens to be a compound called urea. You don't have to know that. So since it's molecular, it's only multiplied by 1. So with respect to colligative properties, this solution still only has 2.4 molal. So now that we've looked at how to identify the numbers, let's look at the other part, which is the vapor pressure lowering. Well, the vapor pressure lowering has to do with what's called Raoult's law. Kind of like Ralph, but Raoult's law. And it's the determination of the concentration of the solution. Now, if you'll notice, it's the mole fraction of the solvent multiplied by the pure solvent. So basically, don't forget that this is all solvent-based. Why? Because remember, solutes are non-volatile. So they're not going to have a vapor pressure associated with them. So how would we use this? What's the pressure of the solution of a sucrose solution at 25 degrees where the mole fraction of water is given and the standard pressure of water? Remember, the degree symbol indicates that that's your standard. So in this case, standard, that's going to be your pure solution. So it's pressure of solution is equal to the mole fraction of the solvent times the pressure of the pure solvent, which in this case, that would be your mole fraction of water times the vapor pressure of pure water. So if we look at it, we're given that 0.986, and the water is 23.76 millimeters of mercury. That means that we get a whopping is equal to 23.42736 millimeters of mercury. Okay, now one other trick. Let's play a game. Let's say we had sugar water. So let's say that over here, and this is a little side note, so this is not the main problem. If we're told that our pressure of water will still keep the same amount as 23.76 millimeters of mercury, but we're told that the mole fraction of our, and let's say sugar water, our sugar is equal to 0.25. Then that means that the mole fraction of the water, since it's only 2 components, has to be 0.75. Because the total mole fractions has to equal 1. So in this particular case, your pressure of your solution would equal to 0.75 times 23.76 millimeters of mercury. Now, I just made that up on the spur of the moment. You'd think I would stop doing that, but oh well. So when I do the math, I get 0.75 times 23.76. That's 17.82. Okay, the point I'm really trying to make is if you're given the mole fraction of the solute, you can easily convert it to the solvent. Okay, so that's being given the amount. And this one, ethylene glycol, uses the antifreeze. Ethylene glycol is a molecular compound. So when you're looking at the particles, you would multiply it by 1. What's the vapor pressure of water above a solution of 100 milliliters of ethylene glycol and 100 milliliters of water? Densities are given, etc., and we're given the pure water at 90 degrees. So, in this particular case, we've got to figure out which one's major, which one's minor. Well, we're given 100 mils of each one, so the easiest thing to do is we're going to have to calculate the moles. Okay? And we're shown that the density of ethylene glycol in water. So basically, if we want the moles, and for ethylene glycol, I'm going to call it ethgly. Okay, so if for the moles of ethylene glycol, we're going to start with the amount given, which is 100 milliliters. And we're going to use our density, which is 1.15 grams per 1 milliliter. And we'll need the molecular weight, which is 62.05764 grams per 1 mole. So if we do the math, we get 1.85312 moles of the ethylene glycol. So we're also going to need the moles of water. And again, we're going to start with 100 milliliters. But remember, for water, the density is 1 milliliter is 1 gram, or 1 gram per milliliter. And it's 18.016 grams per 1 mole. So we end up with a whopping 5.55062 moles of water. Well, that immediately tells us that our solvent is going to be the water. The solute is going to be the ethylene glycol. So the total moles are equal to the 1.85312 plus the 5.55062, which comes out to be a whopping 7.4037 moles total. So our mole fraction of water, we're not interested in the ethylene glycol because it's a solute. So that would be 5.55062 divided by 7.4037. Both of these, remember, are moles. So this is the mole fraction. So we get 0.74971. So pressure of our solution is going to be equal to the mole fraction, in this case, of our solvent, which is water, times the standard pressure of the water at that temperature. So that's 0.74971 times 525.8. And remember that mole fraction has no unit, so you keep the unit of the pressure. So you're going to end up with 198. Can't read my own writing. 98 millimeters of mercury. Okay, so that would be our mole fraction. Now this is a little more complicated than the previous one because in this one you have to go ahead and calculate the concentration as you go. Okay, so we'll continue on. Ideal solutions with 2 or more volatile components. This is a refinery, so you can look at separation of things via distillation. And we're going to get to the math related here in a minute. But before, let's finish out the theory. The vapor pressure lowering results in 3 things that we're going to look at. Boiling point elevation. That means that you increase the temperature of a boiling point if you add a solute to it. Freezing point depression, you're going to decrease the temperature of the freezing point. And you know this easily because in the winter, if they're trying to get rid of ice on the road, they salt the road. Well, why do they do that? Well, they do that because once you add the salt to the ice on the road, it makes the freezing point much less than 0. And then we're going to look at osmotic pressure effects. Osmosis is the movement of a pure solvent through a membrane. more about that in a lot more detail. If you've taken a biology class, you've probably already seen osmosis, but we will look at it in much more detail later. But we're going to look at these effects as we go. Now, if you need to visualize this, this is a phase diagram. There are two of them, and so the net effect is that the black line is the original. And so the blue line is what happens after you add a solute. Okay, and so if you look at the graph, it changes everything. Your triple point decreases, your freezing point decreases, your boiling point increases, and everything changes. So this change in temperature, they've got the change in boiling point there and the change in freezing point there, is a function of a constant. More about it in just a second. Okay, but let's go back to the visual about why and how Raoult's law works the way it does. It operates on vapor pressure lowering, and how this works is in a pure solvent, you can only evaporate from the top layer. So up here we have 1, 2, 3, 4, 5, 6, 7. We have 7 particles. Okay, we have 7 on this side as well, but on this side, all 7 are solvent. On this side, only 1, 2, 3, 4, 5 are solvent. Now, when evaporation occurs, it only occurs with the solvent, and it only occurs with the solvent from the top layer. So what happens is over time, the net effect of Raoult's law is that all of the solvent goes over to the solution. So if you set this up in a bell jar, which basically this means you're isolating it, then the net effect is over time, you end up with all the particles in the solution, not in the pure solvent. And the reason why is that here we have 7 solvent particles evaporating. Over here we only have 5 solvent particles evaporating. But because you can only take the solvent from the top layer, but when you condense, and that's rate of evaporation, when you condense, you don't care what you hit when you come down. You only care that you come down. So you're coming down at exactly the same rate. So the net effect is you end up losing more in the pure, but you gain the same amount on both sides. So because you keep losing more, it ends up all on the solute side. So you would see that over time. Okay, so to put that into words is solution versus the rate of the pure solvent. What you're looking at is the rate of evaporation versus the rate of condensation. And so what happens is the rate of evaporation is less for the solute, or more, for the solution, and it's more for the pure, but the rate of condensation is the same for both. So you keep losing more particles on the pure side, but they keep coming back in. Now, the other factor you have to remember or think about when this occurs is that not everything is going to separate ideally. So, for example, if we look at these two species right here, we've got sodium chloride and HiO3. Ideally, they should separate into 2 particles. But if you notice, this is closer to ideal. Ideal. I don't think that's spelled right. Okay, it's closer for the ideal than down here than this one. And the reason why is the charges are +1 and -1, so plus and minus. And here they're +1 and -1, so the charges are either the same. The only difference here is we have a size problem. Okay, so what we find out is as size increases, then there's less separation. This is what the Hoff factor tells you. And the Van Hoff factor is I, and it's 1 for non-electrolytes. Okay, so that's one factor. I'm going to change colors so that we differentiate. And if we look at this species here, and we can go with this one, these two right here. The difference here is that this one's aiming for 3, so this one's 0.5 off the ideal, and this one's 0.3 off. And the question here is why? Because as you increase charges, you decrease separation. Okay, so we go from +1, -1 here to 2 plus and 1 minus, but there are 2 of them. So we have a factor going on here, and so you can see this continue to go up if you increase, if you have the same charge on this side, but you have a 3 plus charge to a 2 plus charge. Again, this is 0.3 off and this is 0.8 off. So we can look at this, and as you look at the charges and you look at the size of the particles, those will have huge effects. Now, if we take the exact same solution, which we have here, so we have the same compound, we're going to differ by concentration. So if you'll notice, this one is closer to ideal, which is 2, than this. And if you'll notice, so there are more particles here. This is more concentrated. So you can say that the more dilute it is, the closer to ideal. And we'll get to why that is on the next slide. So this tells us why we're not seeing full dissociation. Now, when we work problems on the test, etc., I'm going to be specific in terms of, I may ask you a problem where which one would be closer to ideal and why. That would be a Van Hoff factor problem. If I ask you just a freezing point or a boiling point problem and it's got a salt, I'm going to assume it dissociates completely, okay? Because you have to know how much it dissociates based on experimental. Now, this slide combines all 3 again. And I, which is the Van Hoff factor, I remember is the Van Hoff factor, is closer to ideal when the solutions are dilute, when ionic charges are small. Remember, as they get large, they get farther away from ideal, and the ionic sizes are smaller. And the reason why is something called ion pairing. And what this really boils down to is the ability of the ions to separate. And if they're very large, separate, I misspelled that one, separate, okay? And if they're very large, or if they have a large charge or whatever, they act as one ion pair as opposed to splitting up into separate ones. We call this ion pairing. And ion pairing is the reason why the Van Hoff factor is not always ideal. Why some solutions are much less than what they should be if they split up totally. So this is actually really common, and this occurs everywhere, but these are the main reasons why they would not separate, so they would not give you an ideal value.